Ever pondered what's happening in the world smaller than an atom? Welcome to the quantum world. This is a realm where the very fabric of reality is woven with threads of probabilities, where particles can be in multiple places at once and can even influence each other across vast distances. Quantum physics, a field of study that emerged in the early 20th century, seeks to explain these strange phenomena. The quantum world is a stark contrast to the familiar world described by classical physics. Unlike the predictable nature of classical physics, quantum physics is filled with uncertainties and peculiarities. It's the science of the very small, the particles that make up atoms and the forces that hold them together. It's a world full of surprises and paradoxes, where the rules of the macro world don't apply. Quantum mechanics, a key part of quantum physics, is known for its weirdness. It's like stepping into a world where the impossible becomes possible. Prepare to dive into the fascinating world of quantum physics. In the quantum realm, things behave in ways that defy our day-to-day understanding. This is a world where particles can be in two places at once, where they can spin in two directions simultaneously, and where the mere act of observing can change the reality. Welcome to the quantum world, a place where the standard rules of physics take a back seat, and the peculiar takes the wheel. The first principle to grapple with is superposition. It's the idea that quantum particles can exist in multiple states at the same time until measured. Think of flipping a coin. Until it lands, it's neither heads nor tails but both. The same goes for particles in the quantum world. They can be here, there, everywhere, or nowhere, until someone or something makes a measurement. Next up is the concept of quantum uncertainty. This principle, introduced by Werner Heisenberg, states that we can never know both the exact position and the exact velocity of a particle at the same time. The more precisely one measures one quantity, the less precisely the other can be known. It's like trying to catch a slippery eel in the dark. The more you focus on where it is, the less you know about where it's going. Conversely, the more you know about its speed, the less you know about its location. These concepts, superposition and quantum uncertainty, challenge the classical physics principles we're accustomed to. They're not just abstract theories, but have been proven in countless experiments. In the quantum world, particles can be waves, waves can be particles, and the act of observing can change the outcome. So what does this all mean? Well, it means that our understanding of the universe is incomplete. It means that there are layers of reality that we're only beginning to scratch. It means that there's an entire universe of possibilities waiting to be explored. Quantum physics, with all its oddities, is indeed a universe of its own. So, buckle up as we delve deeper into this fascinating world in our next segment. Want to see quantum weirdness in action? Enter the Double-Slit Experiment. Now imagine a wall with two slits. We're going to fire particles of light or photons at this wall. What would you expect to see on the other side? Common sense might suggest two bright lines directly behind the slits, right? Well, that's where things get a little strange. Instead of two lines, we see an interference pattern, a series of light and dark fringes, as if the photons were waves that interfered with each other. This is where the term wave-particle duality comes into play. It seems that light can behave as both a particle and a wave. But hold on, the plot thickens. Let's slow things down and send photons through one at a time. Surely each photon must go through one slit or the other, and we'd end up with two lines again. But no, we still get an interference pattern. It's as if each photon is interfering with itself, going through both slits at once. This is one of the cornerstones of quantum mechanics, the principle of superposition, which suggests that a particle can be in multiple places at the same time. And now, for the grand finale. What if we place detectors at the slits to see which one the photon goes through? We do that, and suddenly, our interference pattern disappears, replaced by two lines. It's as if the photons know they're being watched and decide to behave like particles again. This is known as the observer effect, where the act of observing changes the outcome. The double-slit experiment is a perfect demonstration of the quantum world's eccentricities, where particles can be in many places at once, and reality seems to change when we're watching. It challenges our everyday understanding of how the world works, and thrusts us into the realm of the weird and wonderful. The double-slit experiment beautifully illustrates the strange and paradoxical nature of quantum physics. It reminds us that at the quantum level, the universe is far more mysterious and fascinating than our human-scale intuition can ever conceive. Imagine two particles connected, no matter the distance between them. That's quantum entanglement for you. In a world where everything seems to abide by the laws of space and time, quantum entanglement dares to defy. It's a peculiar phenomenon where two or more particles become intertwined or entangled in such a way that the state of one can instantaneously affect the state of the other, regardless of the distance separating them. This isn't just across the room or even across town. We're talking about particles that could be light years apart, yet they remain mysteriously connected. This concept goes against our everyday intuition and even perplexed the great Albert Einstein, who famously referred to it as spooky action at a distance. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, proposed a thought experiment, now known as the Einstein-Podolsky-Rosen paradox, to challenge the idea of quantum entanglement. They argued that quantum mechanics must be incomplete since it allows for such spooky correlations. However, numerous experiments have since proven Einstein wrong. Quantum entanglement is real, and it's one of the cornerstones of quantum mechanics. But how does it work, you might ask? Well, that's where the magic of quantum mechanics comes in. When two particles become entangled, they lose their individuality and, in a sense, become one entity. If you measure one of the particles, you instantly know the state of its entangled partner, no matter the distance. It's as if the information is teleported instantaneously, defying the speed of light and the barriers of space. The implications of this are profound and extend to realms like quantum computing and cryptography. It could revolutionize how we transfer information and secure our digital world. But let's not get ahead of ourselves. Quantum entanglement, like much of quantum mechanics, is still a mystery we're trying to unravel. It's a concept that defies our understanding of reality, pushing the limits of what we thought was possible. Quantum entanglement, defying the limits of space and time, truly boggles the mind. From quantum computing to teleportation, the quantum world holds endless possibilities. Let's kick things off with quantum computing. Traditional computers use bits, ones and zeros to process information. Quantum computers, however, use quantum bits or qubits. A qubit can be both 1 and 0 at the same time, thanks to a quantum quirk known as superposition. This means quantum computers can process a vast number of possibilities all at once, making them incredibly powerful. Imagine solving complex problems or running simulations that would take traditional computers centuries, in just seconds. That's the potential of quantum computing. Now let's talk about quantum cryptography. It's all about leveraging the principles of quantum mechanics to secure communication. Quantum cryptography uses the Heisenberg uncertainty principle, which states that you cannot measure both the position and the velocity of a particle without disturbing the system. This means if a third party tries to eavesdrop on a quantum encrypted message, it would disturb the system and alert the communicating parties. In a world where data security is paramount, quantum cryptography could be the ultimate defense. Finally, let's teleport. Well, quantum teleportation to be precise. Now, I'm not talking about beam me up, Scotty teleportation. Quantum teleportation is about transferring the state of a quantum particle from one place to another, without any physical movement of the particle itself. This could have groundbreaking implications for data transfer and communication systems. It's important to note that these applications are still in their infancy, with many challenges to overcome. Quantum computing requires very specific conditions to function. Quantum cryptography needs a reliable quantum internet, and quantum teleportation currently works only at microscopic levels. But the potential is there, and scientists are relentlessly working to turn these quantum dreams into reality. The quantum realm, though mysterious, holds the key to technological advancements we can only dream of. So, there you have it, a brief journey into the quantum world. We've unveiled the quantum realm, an enigmatic universe where particles can exist in multiple states at once, only to collapse into a single state once observed. We've delved into the Double-Slit Experiment, a cornerstone that challenged our classical understanding of physics and paved the way for the quantum revolution. We've also explored the mind-boggling phenomenon of quantum entanglement, which Albert Einstein famously dubbed spooky action at a distance, where particles, no matter how far apart, can affect each other's states instantaneously. Additionally, we've touched on how these quantum peculiarities are not merely academic curiosities, but have real-world applications, promising advancements in fields ranging from computing to cryptography, from medicine to material science. The quantum world, strange and fascinating, continues to challenge our understanding of reality. It's a journey of discovery that never ceases to amaze. Thanks for joining this exciting voyage into the quantum universe.